perspective on how the Kubernetes project is laid out. Like I said, I'm not a Kubernetes developer, so it's going to be fairly limited in its scope. But you really need a good map if you're going to figure out where you're going in the code base. And then we have 2 missions to go on to find some really cool technology. And then I'll wrap it up with a few lessons. Any good scavenger needs really good tools. So these are the tools that I use. I call them the 5 Gs, Git, grep, Google, Godoc, and then go run test.go. Basically what I mean by the last one is sometimes it's easier for me to explore the libraries in Kubernetes or in any large Go project by writing some simple throwaway scripts than rather than trying to sort of do it fully within the context of my Go project. So that's an approach that I take a lot, and I'll demonstrate it. Let's see, in the bash on the left, it's a little bit of pseudo script. I don't actually run that often, but when I want to explore the Kubernetes codebase pinned to a specific revision, I'll check out the main repo, and then I'll go through and check out all the staging repos and advance them all to the revision that I want and have like a cohesive view of the code that way. Cool. Here, I'm going to just get my phone out so I don't run over time. Cool. OK, so let's talk about Linkerd real quick. So Linkerd is a service mesh. It's a CNCF project. It has lots of users, and it provides observability, reliability, and security for your applications running on Kubernetes. There's a lot of other talks you can go to learn more about Linkerd, but I will sort of just talk about the part that's relevant to this talk right now. So Linkerd is divided into a control plane and a data plane. The data plane consists of proxies that run alongside your application. They use the Kubernetes pod model, and the proxies handle all inbound and outbound traffic for the application. And then the proxies receive their configuration from a control plane, and the control plane also pulls all the telemetry data out of the proxies so that it can be displayed in the web UI or the CLI, that kind of thing. So this is sort of the overall architecture of Linkerd. The control plane, the proxies are written in Rust in the data plane. The control plane is written in Go. And there are a lot of parts of the control plane that really are built on top of Kubernetes, and I'm going to focus on 2 of them in this talk. The first one is the CLI. So we have a Linkerd CLI. It's very similar to kubectl. And the second one is the tap server. So tap is a feature that allows us to tap into live traffic, and it receives a bunch of raw routing data from the routers, and it needs to make sense of it. And it's written in Go. So a lot of things in the controller pod operate like Kubernetes controllers. So if you're familiar with those, that will help. OK, here we go. I have sort of bit off an enormous task with this talk, which is to talk through somebody else's code base and to throw a lot of code up on the screen and then hopefully make sense of it. So hopefully bear with me. I hope it's legible. I'm going to give you sort of a quick layout, and then we'll dive in from there. OK, so we'll start at the Kubernetes project. It's the original repo. I guess it looks like that when you ls it. There's a lot of stuff here that I don't understand. Most of my entry points, though, for the project are through either the command directory, the CMD, which contains all the mains for all the processes that run in Kubernetes. So this has the controller manager, the API server, the kubelet, kubectl. It's kind of like the mains for all of those processes. And then a lot of the meat of the implementation of those processes lives in the package directory. And there's a lot of other stuff in the package directory, but that's sort of where I start. And then I am not too familiar with the history of the Kubernetes project, but I take it at some point they decided to split it up into multiple separate projects, and those projects ended up in the staging directory. And in order to sort of continue to build the project sanely, the projects in the staging directory on publish are published out to other repos, but they're sort of developed in the main repo, I think. But there's a lot of stuff in there if you dig into the staging repo. So these are all separate projects that live in separate repositories, but work in coordination with Kubernetes. And that's not all. If you look even farther, there's more projects that are in the case.io org that started outside of the repo itself, so they aren't in the staging directory. So we're not just talking about the Kubernetes repo, we're talking about 40 of these projects, basically, that we could dig through and rummage around in. But I don't actually know a lot about all of those projects, so I will stick with the ones that I'm familiar with, which is CLI runtime for building kubectl and kubectl-like commands. It seems relevant to the Linkerd project. Client Go, which is the main repo for interfacing with the Kubernetes API. And then that's also very tightly coupled to the API and API machinery repos. API has the schema for the API itself. It's a lot of protobuf. And API machinery is the libraries and interfaces for interacting with the API. And then we use a couple other libraries too, but we're not going to talk about that in this talk. OK, so we have made it to our first scavenging mission into the Kubernetes Codebase. There is a very common pattern when you use Linkerd of injecting the proxies. So I mentioned that the data plane has these proxies in your pod model, so we call that injection when the pod, the container for the proxy gets put into your pod spec. And so typically the way that works is you would run Linkerd inject on your manifest, and then it would modify your pod specs to include the proxies, and then you would pipe that to kubectl apply, and then it gets set up in your cluster. And so that way you have all of your apps running with the proxies. And so this is like a very common pattern. Like if I have a hello world manifest, then I would inject it and then apply it. And you can see here that the first 4 lines of output come from Linkerd, and the second 4 lines of output come from kubectl, and they do not look the same. And this is the kind of thing that drives me crazy. So like, why is it that kubectl prints deployment.extension/hello, whereas Linkerd prints deployment hello, in quotes? Clearly there's code somewhere in the domain of kubectl that mashes these strings together in some way, and we're not doing it the same way. But we probably could if we could just find the code that does that. So that's kind of what I set out to do one day. And so we can see if we can fix it. OK, so we're about to enter the zone with all of the amazing alien technology. Like I said, I'm going to put a lot of stuff up on the screen, and I hope it's sort of coherent to walk through it. And at the end, we can follow up with any questions if you have them. So we start our journey in the Kubernetes repo, namespaces. So for our very, very rough implementation of the find pod by IP, we can take the list all pods approach, where we create a new config, we call list pods, and then we just iterate through every pod, and we return the one that has the matching IP. I am going to rate this approach 3 frowny faces, because it is very inefficient. Every time you need to look up a pod by IP, it doesn't make sense to pull every single pod and every single namespace and try to find it. And we can do a lot better. And we can do a lot better without a lot more sophistication from the Kubernetes API, because Kubernetes also includes watching. Every API endpoint has a watch as well, which will send you incremental updates as things change. So this approach is a little more complicated because we need to have a map with concurrent access that we maintain in memory of pods by their IP address. So that is this struct. It has a mutex, and really it's just a map of string to pod. 2 very basic functions, one to add things to the map and one to retrieve things from the map. And with that, we can sort of rewrite our list pods approach to set up a new map and then call watch. And then in a separate Go routine, we can process the watch events and populate the map. And then once we start the Go routine, we just sleep for a second, because let's hope that that's how long it takes for all the watch events to propagate through and for the map to be completely populated before our script proceeds. And then after that, we can just retrieve from the map, and we are able to return the pod. This approach gets 3 neutral faces because, well, let's sleep for one thing, but it's also just sort of a lot of machinery, and it's also hard to know when the map is fully populated. And if we make a mistake processing our watch events, there's no type of reconciliation, right? We could end up like really out of sync with what's actually in the API. So at this point in the development process, like our group starts to think like, well, there's probably a better way to do this. And we start using a different scavenging tool that I like to call Google, where we start just fumbling around for how to cache responses with Client Go. And that takes us to the cache package from Client Go. And this is a big package. Package cache is a client-side caching mechanism, and then it is useful for reducing the number of server calls you'd otherwise need to make. Sounds great. Reflector watches a server and updates a store. less clear what that means. And then 2 stores are provided, one that simply caches and one that acts as a FIFO queue. So anyway, I think we're in the right place. So at this point, I kind of scroll up and down the page, and I get some information. So package cache, store is an object interface, queue is like a store, but there's also a heap in here. There's a reflector, which watches a resource and updates a store. There's a thing called config, which produces a controller. Controller is not documented at all. I actually still don't know what a controller is from the cache package. But there's something called an indexer. And hey, we were building an indexer in our previous implementation. And it's a storage interface that lets you list objects using multiple indexing functions. It sounds like we're on the right track. And new indexer returns an indexer implemented simply with a map and a lock, which is very similar to what we were doing on our own. So maybe we can reuse this code. So at this point, I'll go back to the grep scavenging tool and search the code base. And actually, not a lot of places are using the new indexer function. But the kubelet is, and if it's working for the kubelet, it's probably good enough for us. So we can look at that implementation. And here it calls new indexer, and it creates an index based on the namespace of the service, I think. And rather than go through this whole example, I'll just show you how we could update our script to take advantage of all of this technology, which is the cache indexer approach. First thing we need is an indexing function to index pods by their IP. So it'll receive an object, cast it to a pod, take its IP address, return that value. And then with that, we can create our indexer with our pods by IP func. And then after digging through the cache package more, we discover that we also need something called a list watcher, which can list and watch the pods endpoint. And then we need a reflector to take the updates from our list watcher and update them in the indexer that we provided it. And then we go ahead and run the reflector in a separate Go routine. And every 100 milliseconds, we check to see if the reflector's last resource version has been updated, which tells us that it's fully synced. So now we're no longer doing an arbitrary sleep, at least. And then when it's fully synced, we can proceed with the script, and we can find the pod by IP address. And I will just tell you that this seems pretty complicated. So it gets my 3 thinking face emoji. This works. And we did this in the Linkerd project for a long time for a lot of different objects, and it totally works. It has all of the features that we need. It has reconciliation. It has full caching. You can also add event handlers to sort of act on different types of updates. But there's a better way. And I found out about that better way by watching TGIK, which is Joe Beta's Friday afternoon, like, let's do stuff with Kubernetes thing. And he starts to build a controller, and in it he uses something called shared informers. It's in the screenshot here, but let's enhance it real quick. Basically, you create a new, another thing that he uses is new config or die, which we were not using in our own code base, but it's pretty fun, so we can improve our script with that. And then, he creates a new shared informer factory, and from that produces informers for various types of API objects, like secrets and namespaces. And in order to not run out of time, we'll just rush into this. So this is now the way we've updated our code. So we have our new config or die. We create our shared informers. We grab the pod informer, and we add an indexer to it using the same pod by IP index function that we had already created. We call shared informer start, and then there's actually a cache utility that we found in the cache package that lets you wait until shared informers has synced. The implementation of that is exactly like the implementation we had. It just checks every 100 milliseconds to see if it has synced. But it's a lot less code in our own code base. And then at that point, it's able to read the IP from the index. So I would say we have found it. This is the trove of alien technology that we can really use to our advantage. And there's a couple things that we get for free by adopting shared informers. One of them is that you can configure shared informers to run in restricted mode. So we had a need to run our control plane with limited RBAC permissions. It would typically read all resources and all namespaces in the cluster, but if we wanted to run it in a single namespace, we would have to sort of make sure we're not trying to read any objects from any other namespaces. And you might think that that's like a lot of code, but shared informers already has an implementation that's restricted to a single namespace, and this is the entirety of the change to have all the existing code work in a single namespace. So it really helps us configure it in that way, and there's other ways that you can configure shared informers too. And then the other thing you get is straightforward test fixtures. So if you're already using the Kubernetes client interface, there's a really good like a fake client that you can use that you can pre-populate with API objects, and then those will be returned immediately. So in this example, I have just a stubbed IP address, and I create a fake pod associated with that address, and when I initialize the client, I pass in the pod, and all the rest of the code runs as expected, and it's able to find the pod by IP with just that amount of change in the script. Okay, so I just have a couple more minutes, so stick with me, and we will go through the finale. But you know, I think we did a good job here. We got some intelligence about the Linkerd Codebase. We sort of set up a rough mental map of the Kubernetes zone, planned out a few routes, executed on those routes, returned with some interesting technology, and used some tools of the trade, Git, grep, Google, Godoc, that kind of thing. So at the end of all of this, I wanted to leave you with just a few more thoughts. One of them is research in advance. Like, a lot of this information that I have told you is out there in bits and pieces on the internet. It's in talks, it's in blogs. You know, I don't actually have my finger on the pulse of what the Kubernetes project is doing, so it's a little hard sometimes to just jump in cold turkey. So it's helpful, I think, to sort of do some scavenging outside the code base before you really dive in full force. Yeah, another thing is reusable examples. So in the staging directory of the project, there's all these libraries. So Client Go is one of them. Client Go has this examples directory that's really rich for people just getting started with that library. It would be great to see an examples directory for every other staging project in the repo that shows how to use that project in isolation from the rest of the projects. For instance, CLI runtime could have an example project of building like a really small CLI that interacts with like Kubernetes, that kind of thing. Another point to make is sort of based on my combing of the cache package, Godoc is maybe not sufficient for fully documenting how all the pieces of a package fit together. I think it's really good for documenting the individual pieces, but if we could figure out a way to get kind of a higher level overview and steer people in the right direction, I think that would be really helpful. And in some cases, I think it would be good to break up the packages into smaller pieces. It's not like an ultimatum, but I do feel like it's a little easier to wade through some of these packages if they come in a little smaller chunks. At least that's been my experience so far. So anyway, so that's all I really have to say on the topic. I really appreciate you coming to the talk. If you want to learn more about Linkerd, there is a booth in the booth area. And yeah, I'll be around off the talk. I'll be at the booth the rest of the day. And like I said, I really wish you a lot of luck as you dig through this treasure trove of technology. So thanks.